Since the earliest moments when human consciousness extended beyond immediate physical surroundings, humanity has been captivated by one seemingly simple yet profoundly cosmic question: what is the speed of light? The answer did not arrive as a sudden flash of genius but emerged through an arduous 3-century journey marked by fundamental errors, brilliant breakthroughs, shifting cosmological models, and the relentless evolution of experimental science. This is not merely a tale of numbers and equations but an epic of human perseverance in imposing measurable order on the mysterious chaos of nature. For more than 2 millennia, Western thought was dominated by Aristotle's intuitive assertion that light propagates instantaneously. Everyday experience reinforced this view. When a lamp is uncovered, illumination appears immediate. This belief remained unchallenged until the precise astronomical observations of the 17th century began to reveal cracks in the doctrine of instantaneity. The first serious attempt to measure the speed of light came from Galileo Galilei in the early 17th century. Working on hills near Florence, Galileo stationed 2 assistants at a known distance, each equipped with a shielded lantern. One uncovered his light, and the instant the second observer saw it, he uncovered his own. Galileo hoped to time the delay between seeing the distant light and the return flash. The experiment failed to yield a finite value, but Galileo wisely concluded that if light had a finite speed, it must be extraordinarily high, far beyond the sensitivity of human reaction time and the crude timing devices available. His humility and rigorous methodology laid essential groundwork for future investigators. The first convincing evidence that light travels at a finite speed came not from earthbound experiments but from the heavens. In 1676, Danish astronomer Ole Romer, working at the Paris Observatory, noticed systematic discrepancies in the observed eclipse timings of Jupiter's moon Io. When Earth was moving away from Jupiter in its orbit, Io's eclipses appeared progressively later than predicted. When Earth approached Jupiter, the eclipses occurred earlier. Romer correctly interpreted this as the additional time light required to cross the widening or narrowing gap across Earth's orbital diameter. Using the best estimates available for the size of Earth's orbit, he calculated light took approximately 22 minutes to cross the full diameter, yielding a speed of roughly 227,000 kilometers per second, about 25% higher than the modern value, yet revolutionary because it proved light was not instantaneous. His colleague Christian Huygens refined the calculation and popularized the result. Half a century later, in 1728, English astronomer James Bradley provided independent confirmation through the discovery of stellar aberration. The apparent position of stars shifts slightly over the year because Earth's orbital motion, approximately 30 kilometers per second, combines vectorially with the finite speed of incoming starlight. Bradley measured the maximum aberration angle of about 20.5 arcseconds and derived a light speed of approximately 301,000 kilometers per second, remarkably close to today's accepted value. These astronomical methods, while groundbreaking, were indirect and limited by uncertainties in solar system distances. The 19th century brought the quest back to Earth with laboratory-scale experiments. In 1849, French physicist Hippolyte Fizeau achieved the first successful terrestrial measurement using a rapidly rotating toothed wheel placed between a light source and a distant mirror 8.6 kilometers away at Cheresnes. By increasing the wheel's rotation speed until returning light was blocked by the next tooth, he calculated light took about 55 microseconds for the round trip, giving 315,000 kilometers per second, only 5% high. 1 year later, in 1850, Léon Foucault improved dramatically on Fizeau's design by replacing the toothed wheel with a rapidly rotating mirror. Light traveled to a fixed mirror several kilometers away and back. The returning beam was deflected by the small angle the mirror had turned during transit. Foucault's initial measurement yielded 298,000 kilometers per second. Crucially, he later adapted the apparatus to compare light speed in air versus water, finding it slower in water, a result that decisively refuted Newton's corpuscular theory and supported the wave theory of light. The quest for ever greater precision became synonymous with the career of German-American physicist Albert Abraham Michelson. From the 1870s until his death in 1931, Michelson refined rotating mirror techniques. His most famous series of experiments, conducted between 1924 and 1926, used a 22-mile evacuated light path between Mount Wilson and Mount San Antonio in California and an 8-sided rotating mirror. His final published value in 1926 was 299,792,458 km per second in vacuum, with an uncertainty of only 4 km per second. Michelson's measurements assumed light propagated through a stationary luminiferous ether. That assumption collapsed spectacularly with the Michelson-Morley experiment of 1887. Using an interferometer of unprecedented sensitivity, Michelson and Edward Morley searched for differences in light speed parallel and perpendicular to Earth's motion through the supposed ether. Despite exquisite precision capable of detecting changes as small as 1 part in 10 billion, they found no fringe shift whatsoever. The null result demolished the ether hypothesis and set the stage for Einstein's 1905 special theory of relativity, which postulated that the speed of light in vacuum is constant for all inertial observers regardless of the motion of the source, an inviolable limit written as c. After Einstein, measuring c became less about discovering an unknown constant and more about determining it with extreme precision to test fundamental theories and refine other constants. By the 1950s and 60s, microwave and optical techniques using cavity resonators and early lasers pushed uncertainty below 1 km per second. In 1972, a team at the United States National Bureau of Standards, now NIST, led by Kenneth Evanson, used laser frequency measurements and achieved a value of 299,792,458.05 km per second with an uncertainty of only 1.2 meters per second. This extraordinary precision exposed a philosophical problem. The remaining uncertainty stemmed not from measuring light itself but from imperfections in the definitions of the meter, historically based on a physical prototype bar in Paris, and the second, based on Earth's rotation and later cesium atomic transitions. In 1983, the 17th General Conference on Weights and Measures resolved the issue by redefining the meter such that the speed of light in vacuum is exactly 299,792,458 meters per second. The meter is now defined as the distance light travels in 299,792,458th of a second. The speed of light ceased to be a measured quantity and became an exact defined constant. As of November 2025, the exact value remains 299,792,458 meters per second, unchanged since 1983. This value is now embedded in the International System of Units, SI, and underpins the definitions of length, time, and indirectly many other units. Modern optical lattice clocks and frequency combs routinely achieve relative uncertainties below 10 to the -18, and the fixed value of c ensures perfect consistency between time and length standards worldwide, even on spacecraft or distant observatories. The journey from Galileo's lanterns on Tuscan hills to defining reality itself in terms of light's unchanging speed spans more than 350 years of scientific progress. It required advances in astronomy, precision optics, atomic physics, relativity, and metrology. Today, the speed of light is not merely known, it is the unchanging ruler by which humanity measures the universe, a testament to both nature's elegance and the extraordinary persistence of scientific inquiry.